Shang Chi 9月份. That's right, I said in Chinese, the new upcoming Shang-Chi movie and The Legend of the Ten Rings from Samuel Liu. It's a very fun movie. I'm really excited. With Aquafina, Samuel Liu, Asian American role models. Yay. However, a more exciting situation is going to be the following. I now have a clearer idea what to do for the rest of Algos in Season 2 because, well, my Dell training is almost over and more time for it now, which is awesome. So yeah, today we're going to go over very, very awesome two topics that were actually quite important in my Northeastern Masters and in computer science in general. The Ford Fulkerson network graphs and residual augmenting paths. And of course, ROC, receiver operating characteristic, which is a very important topic in data science. So without further ado, I'm going to show you now my slide deck. And of course, because this is the ROC thing, expect to have some Python coding. But don't worry, this coding isn't something you have to worry about until episode 6, where I actually show you a real good Python coding and a great way to test the coding via sklearn. Let's get down to business and let's continue to learn more about ROC. So yeah, I am sharing my screen. There is Shang-Chi and the Legend of the Ten Rings, AAPI, which is Asian American Pacific Islander, ROC journey. Yep, it's sponsored by Shang-Chi in theaters September 3rd. This guy, this Samuel Liu. The topics. We'll have a quick quiz about ROC. It's nothing too hard. Actually, the reveal of the poll from last episode, we asked you guys, do you want a bonus episode? And do you guys want to even a guest speaker? And I'm happy to say it's actually a tie. So amazing that we have 2 extra episodes now. 2 is better than 1. Though I'll have to warn you guys, it's actually going to be pretty impromptu. So it's not going to be necessarily a predetermined date, given that as a working man, it's pretty fluid how the episodes are going to go now. So do be aware of that. We'll then go over Ford Fulkerson, the very basic, min-cut max flow, something at Northeastern I actually struggled to understand until very recently, reviewing LeetCode algorithms for my interviews. ROC for dummies, the Shang-Chi problems A, B, and C, then problem D, which is technically a small portion of coding, and then the actual coding preview. So here's the quiz question. What is the, well, I already revealed the answer, but whatever. What is the default AOC value under the curve? And ignoring the calculus here, integral of TPR, dx, FPR, whatever, it's just going to be 0.5. And to quickly demonstrate that, I'll annotate something. So I'm going to draw a very simple line. So from very easy, maybe in my case, Worcester County, maybe high school algebra, you have y equals x line and stuff like that, right? So you have y or f of x equals x. This is the line that's 0.5. So for an AOC curve, I'm just trying to draw a random curve here because I'm basically just squiggling at this point. Drawing a random curve here. If AOC curve is this crappy, it's going to be less than 0.5. The ROC value, which is not good. However, if the AOC curve is much better, which I'll draw in blue here. I'll draw in blue here. And for example, this beauty, almost perfect, is not quite equal to 1, but it's definitely greater than 0.5. You want to be here, you want to be in a blue curve, which means it's actually a lot easier to see where the ROC curve is going to be. And of course, the link for all this is from analyticsvidya.com, which is a very good blog website for understanding AOC curves. Now I'm going to clear all this stuff and get back to, the slide deck. So yeah, the poll reveal, we have 31% guest collab, 31% logic puzzle, miscellaneous 26%, and I know you guys might be tiring of me just talking about algorithms all summer. No bonus episode, still a sizable 12%. For privacy reasons, I will not reveal who actually was in this poll. So yeah, So because of that, we're going to have now 2 extra episodes. So it's not necessarily things you have to suffer, like just enjoy whenever. The first episode is really, really simple. It's a bonus episode regards to the zebra puzzle from Albert Einstein, you know, where you have a bunch of clues. You have to like determine, for example, which beer did a German drink, or like, for example, in this case for Pokemon, well, which Pokemon kidnapped Pikachu? It's already a spoiler for the episode. It's a Pokemon related Einstein zebra puzzle. It's actually from Mensa, so really smart guys, aka yours truly, and those guys in Fortune 500s would know how to do these. But it's actually quite easy. It doesn't require any real hard math, it just requires true false tables, that's all. And of course, a guest collaboration regards to decision trees with a very special Northeastern classmate of mine. We'll have a great guest collab on September 21st, 2021, which of course, if you're Chinese American, it is Songzhoujie Mooncake Festival. So yeah, let's get down to business. So Ford Fulkerson for dummies. From the previous definition, let me get to the original episode first. Yes, Ford Fulkerson graphs. So from Wikipedia, Ford Fulkerson is a flow graph algorithm that's defined as follows per Wikipedia. The Ford Fulkerson method, or Ford Fulkerson algorithm, FFA, is a greedy algorithm that computes the maximum flow of a flow network. It's sometimes called a method instead of an algorithm, as the approach to finding augmenting paths, very important, in a residual graph is not fully specified, or is specified in several permutations for different running times. It is published in 1956 by L.R. Ford Jr. and D.R. Fulkerson. That's why I get the name Ford Fulkerson. The name Ford Fulkerson is often used as for Edmonds Karp algorithm, which is a fully defined implementation of Ford Fulkerson method. Okay, that just reads like a bunch of lecture notes, and it's boring, right? You don't want to read anymore. Don't worry, I have it very easy for you. We break it into 3 main parts: max flow, min cut, augmenting paths, and residual graphs. So to simplify all that gibberish, here is the Ford Fulkerson for dummies. We basically have a very simple concept called max flow, min cut. An analogy I have to use for that is the water pipe. So imagine you're in ancient Rome, or you're going and you're visiting Rome pre-pandemic, pre-COVID, and you wonder, how does the Romans actually transfer all those waters between, for example, Rome to like Naples, or to like Florence, or to even Milan or Como, right? Well, the answer is very simple. They use something called aqueducts. And I'm no architecture buff, so here's my best interpretation. We have an aqueduct over here, and we have some water, right? Some water. And with each aqueduct, you basically have like 2 towns, town A and town B. So it's like a bridge, basically. And to make sure the water doesn't, leak out or spill over or even drown the people in the towns, you got to make sure there's some reinforcements in these tubes of water. So the max flow min cut essentially saying, however much water is flowing from town B to A must equal the amount of water from town A to B, which is almost like Newton's 3rd law of physics, right? Every equal action is greater than or opposite to equal reaction. It is quite physics-like, actually. But because we're in computer science, not in physics, we have something called sigma notation, which is the sum of the flow must equal sum of the cut. And this is what we call the conversation rule for max flow min cut. Thank you, Professor Viola from Northeastern Algo for teaching me a good way to remember max flow min cut instead of the crazy, gibberish over here. And now, as I mentioned before, this is basically a residual graph with augmenting paths called Edmund Karp. Yeah, you can try to code Edmund Karp, and we will, but we're not going to do it from scratch because that'll just take too long. And honestly, we're here to teach you how to do algorithms in an easy way and not confuse you any harder. I learned that the hard way for the interviews, coding this all from scratch. And let me tell you, it's not worth it if you don't know what you're doing. And also we have a source node and a sink node for graph G, VE when applying to Ford Fulkerson. That's yet another set of drawings that really show the power of Ford Fulkerson. Here's a little warm-up exercise where I low-key just grab the graph from random. What's the max flow of this graph? What's the min cut of this graph? And what are the augmenting paths? So if you want to get yourself a piece of paper or iPad or whatever, just something to write on and give you guys a few minutes to think about this algorithm. And to actually make it a little more challenging, I won't tell you the answer directly, but rather show you my thought logic to get to the answer. Oh, by the way, just to distract a little more conversation, I heard that actually there's some really cool Bitcoin going on, mining Dogecoins. Those are quite interesting to invest in. And of course, more related to Shang-Chi, actually, one reason I actually want to watch the movie is to really see how does the movie, quote unquote, flow in between scenes. I won't give any spoilers, but that's basically how I want to see the action movie, like in a sequential flow. Not choppy all over the place, like Artemis Fowl, God forbid that movie, you know, like I want to have my childhood not be ruined. So I want to enjoy, you know, the movie as it is. Sorry, yeah. Oh, another very quick hint. S is the source node and T is the ending node. All right, I think besides me blabbing about Shang-Chi, that should be enough time to at least get an answer. Yes, if you have answer 7, you already know what you're doing. So how do we get 7? Well, quite obviously, it's just CT and DT, right? If you do chop these two off, you basically disconnect the graph. There's just no way the graph can reach the sync node T. That node is gone. It's yeeted, it's gone. And that just shows right there the easiness of Ford Fulkerson. This is like the best case scenario. You don't have to really do any real math, just look at the nodes and see where the graph will get cut. Ah, yes, the min cut, which you just mentioned, is also going to be 7. And the min cut set is actually the following. So this is not the answer to the min cut set. The min cut set is actually a set of nodes, CDT. Yeah, CDT. I got this wrong in my Algos class because I thought it was supposed to be a number, but it's actually not. It's actually a set of nodes. So don't make the same mistake. But yeah, the min cut value is 7. It better be same as 7 max flow, but we're in trouble. Basically, I'd be telling you a lie all evening, and I should go back and reduce and retake algorithms otherwise. And you know, not do that. Not a good idea. And augmenting paths, well, the easiest can be P of SACT, where you basically have flow back of 2, then P of SBDT. Oops, that is actually a typo. Oh, sorry, SB DCT, yeah, which is a flow of 1. And it's supposed to be SBDT. I'm going to fix that quickly. If you don't mind, I'm going to fix that issue real quick. That's what happens when you code the opposite while doing work. All right, so we're back to where we started. Yes, SBDT, that's correct. That's going to give a backflow of 1. Then you have SBDCT, which is a backflow of 1 again. And then finally have the longest flow, which is basically everything, SABDCT, which is a flow of 3 from everything. So when you add them all up, you should be getting 7 as well for augmenting paths. Now here's a nightmare case, which I hope none of you guys ever have to deal with, because God forbid, you're gonna basically not have the rest of the year to do this thing. What's the max flow of this graph? Well, let's see. Okay, uh-oh, I can't get anywhere. This graph is infinite. This graph is basically a loop. It's one of the worst cases of Ford Fulkerson. It's called the nightmare case. You basically can't determine the mass flow because it's infinite. And the min cut's also infinite because you have no way to cut the graph because there is no starting and ending nodes. And our venting path is just going to be A, B, C, D for end of time. So yeah, have fun. See you next year. You don't need to worry about any more episodes. Avoid making a graph like this during an interview, because then they'll show the interview, you don't know what you're doing with time complexity, and also just waste a lot of people's time. But it's good to at least know what is the worst case. As you know, during COVID, we have to work the worst case all the time. Now something more fun. Intro to ROC AUC, which is of course the receiver operating characteristic, the area under the curve. So the ROC AUC curve is basically known for signals processing. What does that mean? So it basically means like flipping a switch on and off, like a light switch, or even if you're an NBA fan, LeBron James or the Cavs or Warriors flipping a switch, turning it on. And then when they're in the off season, turning it off. Or the Boston Celtics even turning it on when they need to. We'll just sample all the true positive rate and false positive rates. So TPR here, FPR down here, from a confusion matrix. I told you this could be confusion matrices from last episode, and hopefully you remember what that is. A random guess classifier would just be bad. It's just 0.5, you know, it's just bad. Don't get anything below 0.5 when you're doing ROC AUC, or your model is just crap. And then to basically calculate area in the curve, we use a special formula. We don't use calculus, we use geometry. I'll show you that formula later. So first, I'm gonna show you a real awesome application of Ford Fulkerson that doesn't even require any math, which requires understanding the principles behind it. And it's also a really great interview and one of my final exam questions in Algos, basically. Or related to that. So it says Shang Chi and the Marvel Corporation has hired a computer science co-op from Northeastern to do some econometrics, which is like basically using computer science to metrics to determine economic results, like, you know, stock marketing or loans sharing, or in this case, advertisement marketing for the movie. The company states the following: given an A amount of influencers on Instagram, I should highlight this because it's very important. B amount of promoters on Facebook, C amount of moment lovers on WeChat, and D amount of advertisements on YouTube live stream, which I definitely recommend looking at for MLB games. Each up to IJKL amount of people reach out respectively, write an algorithm that will be able to reach at least each person willing to watch the movie. Once again, I'm going to just simply keep quiet and let you guys think about this for a moment. And this time I will not be yapping about anything. Okay, that should be enough to at least think about a solution, 30 seconds. So here's the solution. It looks like a lot, so I'm gonna just quickly go over it piece by piece. We apply something called a reduction. That will be actually in the final episode of the season, NP versus P reduction. In the season finale, which is gonna be up, I'd say probably before Halloween at this rate, honestly. It's been a slow going given their work and home and stuff. It's been slow going. Anyway, we apply reduction for the Ford Fulkerson algorithm. We deal with I mentioned before, we deal with NP and P reductions in the season finale. But now let's just consider reduction simply as Shang Chi to Ford Fulkerson. We first define the source and sync nodes S and T. We then apply 4 layers of nodes for A, Instagram influencers, B, Facebook promoters, C, WeChat moments, and D, YouTube live stream advertisements. And you don't want to connect the nodes yet because you need to do something very special to them. Then we add I amount of those Instagram nodes, B amount of Facebook nodes. You get the point, like K amount of WeChat nodes and D amount of YouTube live stream nodes, which means they may not all be the same, but they could be pretty equivalent. I less than equal to J, less than equal to K, less than equal to L. In real life, we simply would not have the same amount of nodes because we ask like different people, but it's approximately close. So we'll reflect that here. And now, the fun part begins. Since we're trying to determine if we can reach out to at least one person willing to watch the movie, we create a one-to-many mapping. And if you have done data science work like yours truly, you understand what I'm talking about. So a one-to-many mapping, one dot star. That's what I want to see. A one-to-many, which is abbreviated by the star here. One-to-many mapping. Yes, a one-to-many mapping for each of the nodes and connect them accordingly with weight value of 1 because you're trying to only reach to one person. Between the nodes, and infinity because you don't know how many people they're going to be reached out. Between source and sink to connect to Facebook motor nodes and the WeChat nodes. And then we apply Ford Fulkerson reduction to essentially find the maximum flow, which represents the maximum amount of people we can reach out to watch the movie. And here is the kicker. Assume everybody uniquely ordered a movie. So for example, if you actually ordered a movie, you understand there's like a unique ticket number, or like a ticket encoding, which gets into a bit of crypto. You have to think about, unique hashing and stuff like that. That's what we could do for like maybe crypto. I'm not a crypto person, but that's what we do for crypto. If we don't have that, if there's actually duplicate, like counterfeit tickets or whatever, this thing becomes NP complete because we don't know how to actually determine the nodes to go to. That will become actually something that it can be reduced into Ford Fulkerson again. So here's another thing about algorithms. You can actually reduce a problem to a simpler problem. Hint, hint. If you do leak code interviews, mention that. That will show you actually know what you're doing in terms of procedural decomposition. And isn't life all about making things simple? Exactly. Yeah, as I mentioned before, here's basically the nodes. You have the source node, the sink node, infinity, 1, 1, 1, 1, 1, 1. As you can see, I didn't exactly write all the nodes down because it's rather boring and also defeats the purpose of the one-to-many mapping. And here's a fun question. What's the runtime of this? It's cubic because you have basically a for loop going for each of the possible nodes, another loop going for each of the iteration of nodes, and then yet another for loop to determine if the nodes is yes or no in a linear time. So it's cubic runtime for Fulkerson algorithm. OVE squared. Now we have Shang Chi problem part B. We face some enemies. The first 5 of the 10 dragons. So yeah, the movie is called 10 Rings, but let's just assume dragons, Dungeons and Dragons is like the enemy, D&D. So RLC dragons with each respective AOC of 0.3, 0.4, 0.5, 0.6, and 0.7. So the value of Shang-Chi can defeat these dragons easily given the following confusion matrix of his own ability, and Shang-Chi cannot yet obtain an AUC above 0.5. He's also going for some training, this guy. And here's the matrix, the victory trues and the defeat false. So right away, guys, the true positive is 33 and the false positive is 77. I mean, the true negative is 77. And of course, the false positive is 55 and the false negative is 44. Remember those values on the confusion matrix because the next slide will definitely quiz you on that. Since I realized in episode 3, the math took too long to solve, I just basically deliberately doing the math a priori before the episode. So long story short, I calculated TPR, FPR, TNR, FNR with all the found formulas on Wikipedia. And these numbers are great because they're complements of each other. Like for example, 0.375, 0.625, if you add them up, is equal to good old 1. 0.363 repeating and 0.636 repeating should also approximately add up to 1. And this is exactly why you want to make sure a sanity check. If your TPR is not the complement of your FNR, then you're doing something wrong. And now to calculate the whole thing together, we can actually use the following formula. A triangle portion, trapezoid portion, and combined portion. Now let me draw now quickly another thing to demonstrate what I'm talking about. Let's say this little graph over here is our, ROC curve thing. I'm gonna just draw like a squiggle, whatever. So you have a triangle, you have an ROC curve that looks somewhat like this, right? You have one defined triangle portion here, more or less. And you have one defined trapezoidal portion here, more or less. So you're trying to basically determine the summation of this, of this triangle over here, and then this trapezoid over here. This is an approximation because if you try to actually use calculus and add in these little portions, you'll get the Riemann sum, which then gets to the integral of all that, you know, that calculus gibberish. But we're not here to do calculus, here to do algorithms. So yes, the triangle portion is basically the area of the triangle. It's TPR times FPR divided by 2. That's simple. The trapezoid portion is a little bit tricky. I had to actually go for Stack Overflow to really make sure I understood this. It's a half minus FPR plus TPR over 2, and then minus that combined TPR times FPR over 2. And then the total would simply just be 1/2 minus FPR over 2 plus TPR over 2. And because I don't want to rederive and redo the wheel and get into math mistakes, I just use the total straight up. I'm a rather lazy person when it comes to math. So calculate the total to be half minus this minus that. And well, if you checked out the math, it's 0.0506. So almost very bad. It's almost the same as like random. But do not worry, Shang-Chi will get help in part C. As always, the Marvel characters always level up when they get into later in the movie. So part C, there's something called Master Yi. I know it's League of Legends reference, it's not from the movie, but somebody who I want to call a master to Shang-Chi. Master Yi is ready to upgrade Shang-Chi with the Mortal Kombat finishing move. That Shang-Chi will have to draw the powered ROC curves where his true ability lies. So you're going to do the same. Draw a rough sketch of each AOC curve, including Shang's. If you figure this out, Shang-Chi gets full power at perfect AOC of 1.0, no overfitting required. And just to make sure how good it looks, here's the 1.0 AOC. It's a hyperbola of beauty. This is what you want for any model. This beautiful looking hyperbola. Yeah, this beautiful f of x equals 1 over x business here. You definitely love to see that. You don't want to see a random looking 0.5 AOC. You want to see a nice curving AOC here. This is like the gold standard. But as in life, nothing is perfect. It's very hard to get that type of AOC. I tried it many times, only once with a very advanced classifier I managed to pull that off for my data science project. We'll see that in the finale episode, something related to that, how hard that actually is to get. Hint, hint, it took me a week to figure that out. So if you have a week to blow off, go for it. Anyway, for this graph, we have the colors of AOC, which is a rough sketch. So you have the regular default of 0.5. You have Shang-Chi's, which is a little bit better, 0.506. You have a terrible AOC value of 0.3 and a not so great value of AOC of 0.4. So just a fun scientific fact. The false positive rate is specificity, and the true positive rate is sensitivity. From AI, that's how you basically determine your sensitivity specificity. It's from that confusion matrix. And now we finally conquered the rest of the dragons with AOC levels of 0.76, 0.56, and 0.99, which is almost perfect, respectively, with a little Python work on NumPy, SciPy, Jupyter Notebook. And to make this easy, we're going to use the iris data set for reference. So this reference code is not by me, it's by sklearn, which is great, scikit-learn. But I modified it a bit to make it easy to read. So here we go. Here's the code I made, a little mini code demo I made for this episode. It's really short. It's only one, basically only one Jupyter Notebooks cell. So if you see here, you have AOC comparison values given confusion matrix to Shang-Chi. So if all the imports up here, I add my sources, I don't copy and plagiarize stuff. You want to remove the warning, otherwise you have no idea what you're doing with the curve. And then we basically import the iris data, we binarize the output, which means basically turn the output from multiple classes to just 2 classes, yes and no. And then we basically multiply n features by 100 to reduce complexity of classifiers. Easier to visualize the differences, because the original code has 200, that's like too complicated. Then of course, with any type of data set, you explain the training and testing. 0.5 is not what I would choose, but I'll let it slide for now. It's a little bit too perfect. I would rather choose 0.7, 0.8 actually. That's a little bit better, a little more biased, a little less even Steven 50-50. Yeah, I basically use something called a one versus rest classifier. That's where the one to many basically gets called from, with the kernel value of linear. And that's a bunch of gibberish for like determining what type of classifier to use. And here's something that you should definitely always use in Python coding: FPR, TPR, OC, AOC, dict. If you do not have this, you will have no idea how to debug this portion here, the micro average and ROC area. Because the ytest.revel, this function is very, very quirky. It actually changes the dimension of your ytest and y-score parameters, like inside the array. So basically turns the array from a 1 by n to an n by 1. I told you guys before, debugging is hell in Python when it comes to like arrays, like because it's all about memory and also about pointers and address spaces. You might as well avoid it by just simply adding in your dict array or dict structure as an array as early as you can. You know, like my mentor Don says, no good deed comes unpunished. That's what I meant by that. Like get your ducks in order before you do anything like this. Because I learned the hard way in my Northeastern class. Not to do that, we spent a good week debugging and being mad about it. Not the most greatest way to celebrate my end of masters, to be honest with you guys. And of course, going to have all FPR, false positive rate. And then we interpolate all the ROC curves. This is more basically trying to estimate the best points. And finally, average and compute the AUC. And this is something very familiar. You know, if you do Python, any Python plotting, it's matplotlib. And I decided to only use 3 colors because we only need 3 things. We need the 0.9 ROC curve, we need the 0.56, and we need the 0.76 as well. So let me just run this all quickly through just to make sure this actually runs good, and we'll be done for the episode. Yep, there we go. So this is a really quick and easy and not from my own personal work demo. Episode 6 will do the exact same thing, but with a way more complicated way of doing things and actually show you guys different classifiers like SMOTI and gradient boosting and decision tree. So you guys are getting a sneak preview of my guest episode right there. You know, a nice little discount for waiting so long for this episode. So congratulations, you guys, for having the patience to wait 2.5 weeks for this episode. It's worth the wait. And they had more time to think about what to actually put in here instead of just slap a couple of Jupyter notebooks and call it a day. So yeah, that's it for this portion of the episode. And now preview of episode 6, we're going to just say we're going to code from scratch all of the solution we had earlier. So yeah, see you guys in 2 weeks. Watch Shang Chi and the Legend of the Ten Rings and this, you know, very awesome looking guy, Shamu Liu. And of course, episode 6 will be 2 weeks from now, which is in September. And make sure to like and subscribe and hashtag Shang Chi. So yeah, that's it for the episode 6 for That Was the 10 with Jason Liu. It's been a real great pleasure this summer actually like doing all this algorithm stuff. It's been a nice break from my actual dev work and, you know, monotony of living at home and stuff. So here's a question for you guys. What is it about algorithms, if you have taken that class before, that makes it so tough to pass or so tough to understand? Because I feel like it's like driving a car. If you have like a good instructor, it's actually rather easy. But if you have a bad instructor who pushes you, harangues you, curses at you, and just makes you feel miserable and makes you feel like you're about to fail the class, it's not that easy. So say in the comments or even private DM or whatever, what makes algorithms such a difficult class to pass in computer science? If you guys have any stories, I'd be glad to hear about it. And of course, my guest speaker, hopefully in September around the Mooncake Festival, will also give his spiel about algorithms in Northeastern and why it's not necessarily what you think it is. So anyway, until then, stay safe, you know, be careful with COVID, and watch Shang-Chi movie on September 3rd, 2021. And continue to enjoy the remaining part of your summer. Thank you very much.